Hey guys, so we're going to pick up here with chapter 4. Um, and this chapter is all about the periodic table. Okay, so first we need to have some basic nomenclature to kind of orient ourselves in how we talk about different elements in the periodic table. The groups are vertical columns. Okay, so that's the one on the left here. So like if you look at your periodic table that I've given you, the first group is labeled number 1 and 2 and 3 and on like that. This will be 13, 14. So all of these are different groups, okay? Which used to be, oh, I got off somehow. There we go. There's only 18 groups, okay? These groups used to be called families, okay? Because they are a way of organizing the chemicals by how they react. So the same chemicals react in the same way. So we call that a family. Or rather, the same groups here are going to react in the same way. Periods are across, so the first period is here, the second one is here, on and on like that. Okay, so they're labeled right on the periodic table that I gave you. And in fact, this is not a very good image of how the periodic table looks now because we have filled in all these elements. So this purple line should go all the way across. But this gives you an idea of what the nomenclature, the naming is for each of these categories. So groups are the vertical ones and periods are the horizontal ones. All right, so the story of the periodic table is actually a really epic story. It's a really long and evolved process. So it didn't just appear, as it is today. One of the first versions of the periodic table was proposed by Deschantois, and he was a scientist way, way back in the day. So a quick Google search will lead you to this website about, with some more details about Deschantois' contribution to the periodic table, but basically his idea was published before any of the other ones, maybe somewhere in the 1860s. And the reason he wasn't widely accepted as the inventor of the periodic table is probably because the graph itself, the periodic table he proposed, wasn't included in his original publication. And so then 2 years later, another guy comes into the picture. All right, so let's go back to the slides. Another guy comes into the picture, and he says that the elements we know of, which weren't very many at the time, this is all of them, the elements that we know of should be organized horizontally. So let's take another look here right at Deschantois' version. If you look at the groups that we see in the modern periodic table, they come up in Deschantois' version as well. So group 1 is made out of sodium, well, lithium first, then sodium, and then potassium. So here on this version of the periodic table, they all line up on the same line. And then we turn it into a cylinder so you could see kind of some patterns that are in there. That's what these diagonal lines are. Unfortunately, this was such a complex graph that it was hard to print. And so in order to print it and have the letters be legible with 1860s technology, you had to make the periodic table like 6 feet tall. So nobody really liked this very much, even though it communicates some important relationships, like the fact that everything in group 1 reacts in the same way. Okay, so anyway, so this is like a 6 foot tall periodic table. It's not very convenient. So then in 2 years later, Newlands comes out with his periodic table, which looked something like this. It was coined the law of octaves. Okay, so essentially his argument in his paper was that you can categorize those same families. So here we have, let's see, the lithium, the sodium, and potassium. So instead of being vertical like Deschantois was, we have Newland's proposal to make it sort of a horizontal arrangement here. Same family though, okay. But what he noticed is that when you organize it this way, it appears that there are, categories that happen vertically, and that there's 8 of them. And in his paper, he noticed that, there are like 8 notes on the musical scale, 8 octaves basically. And so he correlated the elements to music. And at the time, he kind of got laughed at because people didn't really like to combine science and art very much. And so Newland's periodic table wasn't widely accepted either. And then the story progresses to Dmitry Mendeleev, who is a Siberian scientist. His story is very interesting. In fact, I have linked some PBS videos, which are actually really well done. Even my kids enjoyed watching them. And one of the things in the video that is explained is that how Mendeleev came up with the periodic table and how critical it was and how difficult it was. But basically, his relationship, the families are still there, okay, but they're vertical again. So we have lithium, sodium, and potassium lined up in the same category. And interestingly, he ended up with 8 groups as well. That's Russian for group. And then 8. Actually, I think it's a translation from Russian. So group 8, just like Newland's periodic table, only he didn't compare it to the musical scale. But Mendeleev went one step further. He was able to show some blank spaces where elements should have been. So these little lines all represent elements that at the time we didn't even know existed. But Mendeleev was able to take every one of these little dashes and calculate some of their properties, like how heavy they would be. That's what the 68 refers to. Even things like how dense they would be, what color they would be, how they're going to react. He predicted all kinds of properties with nearly 100% accuracy. And so this led to a revolution in chemistry. We started to look at different natural substances and try to find the missing elements. And it became a race. Everybody wanted to be first to find the next new element, And a lot of these elements are really important in our modern technology. So for example, hafnium is one of the elements that's represented by these lines. It's not on here. Its symbol is HF. And hafnium is used to make our electronics efficient. So if you don't have a little bit of hafnium, just a tiny bit, in your wires, they get too hot to have phones that are as small as they are these days, the ones that fit in your pocket. So hafnium is an important element that we use quite a lot of, but it wasn't known, in 1869 when Mendeleev first proposed his periodic table. So Mendeleev gets the credit. He's often called the father of chemistry because he wrote one of the most widely distributed chemistry textbooks. Lavoisier actually wrote the first one, but Mendeleev wrote one of the next versions, and it had organized the elements into a logical pattern. But more importantly, again, he predicted the existence of elements that we didn't know about. So that's really the beauty of Mendeleev's periodic table. I really encourage you to watch the videos that I've linked up in Blackboard. They're optional, but they are really interesting, and it helps to remember the dates and the people and how everything relates to each other. So especially if you like watching TV better than listening to lectures, then I definitely recommend that. All right, so in the modern periodic table, we organize things into basically 3 categories, and these 3 categories are actually from the first guy to ever publish a chemistry textbook. All right, his name was Lavoisier, Antoine Lavoisier. The same guy, by the way, who invented the metric system pretty much on his own. It's been changed and modified since then, but he was the first one to propose the idea that we should all have the same measuring system. And so Lavoisier was really important for standardizing science. Also, he got his head cut off because he was a French noble during the French Revolution, so a little bit of a dramatic life. At any rate, so Lavoisier was the first person to publish a chemistry textbook, and there weren't very many elements known at the time, but he did observe that they fell into 2 broad categories at the time that he wrote it. The first category is metals, and the second one was non-metals. Now we know that there's kind of a middle ground where the properties kind of mix a little bit, and we call those metalloids, okay? But you know what a metal is. You're familiar with it. They're shiny. They tend to be solids. The only one that's not actually is mercury, which is a liquid. They're always shiny. They're always conductive. For both electricity and heat. Okay. Other words that we often have associated with metals is ductile. Okay. Ductile means that you can turn it into a wire. So you can take, platinum and stretch it out into a really thin wire, which is useful because that's what we use copper actually to conduct electricity in houses. And another word is malleable. Malleable means that you can stretch it and shape it, like you can make copper into a pipe, or you can make it into a sheet or a wire. All of those things are malleability, sort of like Play-Doh, right? Nonmetals, on the other hand, if you try to form them into a sheet or a pipe or whatever, they just disintegrate. They turn into a powder. So they're not malleable at all. They're very fragile. They do have really high melting points, which means I got to put a lot of energy in to melt them. So things like sulfur, that's a non-metal, and you have to, in order to melt it, you have to heat it up really hot. So you guys saw that in the lab, all right? We did that just the other day when we were doing our experiment about properties of oxygen. You also saw that the sulfur was not shiny. It was kind of a dull yellow color. They don't conduct electricity or heat. So they're exactly the opposite of a metal, which is why we call them nonmetals. All right, and then metalloids, there's only 6 of them, and they're in between the metals and the nonmetals. So let me show you, I'll show you a periodic table in just a second to help you find those 6 elements. Another important fact we need, and this is where, you know, flashcards will come in handy. Okay. I'm going to ask you these in class next week, so make sure that you understand the diatomic elements. Okay, so di means 2, and of course atomic means atoms. So 2 atoms together make these elements, right? Okay, so there's 7 of them, and there's 2 ways you can remember it. The first one is to use this mnemonic, have no fear of ice cold beer. And the reason I like this one, so the beginning of each letter correlates with an element, right? So N is nitrogen, F is fluorine, not iron. A lot of people see Fe and they think iron, but it's just fluorine. There aren't any metals that are diatomic. Okay, you'll notice these are all nonmetals. O is oxygen, I is iodine, C is chlorine. A lot of people confuse this with carbon. I'm not sure why. Carbon is not a diatomic element, only chlorine is. And finally, beer. There's a lot of B elements in the periodic table, so it's bromine. It's not boron or beryllium or any of the other ones, okay? Now, this is also an interesting mnemonic to know because it gives you the state of matter for these elements, all right? So like ice is solid water. So as it turns out, at room temperature, iodine is a solid. It's a bright purple solid. It's actually really pretty. And then beer is a liquid, right? That is also true for bromine. Bromine is a liquid, beer is a liquid. So the rest of these are all gases, okay? So like hydrogen, nitrogen, fluorine, all of these are all gases, okay? So this is a handy mnemonic to remember, have no fear of ice cold beer. And the reason we need to know it is because when I say something like a reaction produces hydrogen, then if you don't understand that hydrogen is not just plain H, it's H2, you're not going to be able to balance your reactions and write the reaction correctly. So we really need to know these diatomics, okay? So make sure you're studying those, make sure you're remembering them. I said there was 2 ways to remember it. So the mnemonic is one of them. Another one is to look at a periodic table. All right, so here's our periodic table. And what's interesting about this is if we start at the nitrogen, we make a 7, all right? So it goes nitrogen, oxygen, fluorine, chlorine, bromine, iodine. We make a 7. That's 6 of the diatomic elements, so they form a 7 on the periodic table. You're always going to have a periodic table around you when you do tests and such, so that's one way you can remember it. So it's those 6, NOFClBri, plus hydrogen, okay? So it's a 7 plus hydrogen. So that's one way you can remember it. It's a handy mechanism to help you with that. All right, so we have specific names for specific families of elements. So for example, this group 1 is shown in gray, and we call it the alkali metal group. The green group is alkaline earth metals, alkaline, okay, so I-N-E, not just alkali. These actually mean completely different things. Alkali metals all explode when you put them in water. We're going to see this in lab, okay? We're going to actually test lithium and sodium. You're going to see it for yourself. But yeah, they're not, whenever you put them with water, they react quite vigorously. Whereas the alkaline earth metals just sort of bubble and dissolve, which is interesting, but it's not the same as fire, okay? So they have similar names, but they're totally different properties. And then in groups 3 through 12 here, from Sc, which is scandium, all the way to zinc, these ones are what we call transition metals, all right? And it includes these groups on the bottom here because these groups actually belong way up here. So if you follow the atomic number, here's 57, that's lanthanum, and we go to 58, which is cerium. So on your periodic table, it has a little line in here, and it indicates that lanthanum is first, then you go cerium, and all the way through here, and then we go back up. This is the half name I was talking about earlier, by the way. All right, so this line is brought down to the bottom because if we had it in here, the whole periodic table would be so spread out, you'd have to have really long paper to print it and still be able to read it. And then of course the one on the bottom, 89 is actinium and 90 is thorium, so that this is where that goes, okay? Let's color code that for you. So actinium connects with thorium like that. Okay, but we're always going to write these down below. We call the first group, the red one I highlighted here with cerium, this one is called the lanthanoid series or lanthanide series. Oid is kind of an old nomenclature, but lanthanide series because it comes after lanthanum. And then the one below that, AC, that's actinium, so we call that the actinide series. Okay, so this whole row here actually belongs right up here in the periodic table, and we call it the actinide series. But that's why the lanthanide and actinides are both part of the transition metals as well. So this whole group in the middle here. And then we have some metals that don't have any fancy name. Okay, so like on your periodic table, there's actually a line in between some of the elements. Okay. It starts off right here at boron, and then it kind of does this stair-step thing right past arsenic and tellurium, and it stops right there. Oh wait, it doesn't stop there. My periodic table just has the bottom row completely filled in, so it just doesn't extend to the bottom row. On our periodic table, these are filled in because these elements are well known. Way back in 97 when this was made, we still hadn't even named 110 and 111 and 112. Right, so the U's are like a placeholder. We've actually named all of these now, but the newest periodic table isn't out. So yours probably has a few elements on the bottom that are not quite shown on there, but they actually do have names. At any rate, these stair step is where the metal and non-metal section divides. So everything underneath the steps, so that is to the left here, is metals. A few of the things that touch the stairs are metalloids, and everything else above the steps is non-metals. Okay, so that's the pattern. Another thing that this periodic table, this version, the reason I like it is because it tells you state of matter, the color of the letter. So mercury is a liquid, gallium is a liquid, or really close to a liquid at room temperature. You can actually melt it in your hand. Bromine and cesium. So those are all the liquids. Everything, mostly there's a lot of solids, right? And then there's a few gases. This group, of course, is called the noble gases. So those are definitely gases. And then there's quite a few up here. Another group name that's not on here is group 17. So you want to jot this down. Group 17 is often called halogens. That's an H, not an N. Or sometimes also called halide. Okay, so that just refers to everything in group 17, fluorine, chlorine, bromine, iodine. Okay, so those are important names to know. There we go. So Lavoisier's arrangement was originally to distinguish between metals and the non-metals, and then later on we developed the understanding that some things are kind of they have properties that are in between metals and non-metals. You know, maybe they're not conductive, but they are malleable. So that's one property from each section. So we call those ones the metalloids. There's only 6 of them: boron, silicon, germanium, arsenic, antimony, and tellurium. Those are the 6. So pretty much if you're touching the staircase except for aluminum, then you're a metalloid. Okay. Everything to the left or underneath the staircase is metals, and everything above it is nonmetals. Okay. All right. So the idea of the periodic table is to organize elements by a repeating pattern. So periodicity means pattern or trend. Okay. And the pattern that was used is to categorize elements by family, which again means to categorize them. Wow, I don't know what just happened. To categorize them by how they react to other substances. They're not categorized by mass. They're not categorized by atomic number. Those things are patterns in the periodic table, but they weren't the reason that we made the periodic table the way that it is. Okay. All right. So again, this is your opportunity to tell me what you remember from the other slide. Try not to go back. This is a recall exercise. Tell me what you remember about what makes something a metal and where it is on the periodic table. And the same thing for nonmetal and metalloids. So pause the video and take a second and just jot down what you recall. Okay, so in our story of the discovery of the periodic table, we actually have to go back even farther, to way back, actually even before 600 BC, 400 BC, which was around 2,500 years ago. In ancient India, they came up with the idea of a particle that was indestructible. So basically you have something so small that it can't be broken anymore. And they had a different name for it than what we use now, but about 200 years later, a guy named Thales of Miletus, who was a Greek dude, hypothesized that atoms might exist. So that idea actually came from ancient India. Thales kind of just named it, right? So he said, okay, well, if you have a particle so small that you can't rip it, it's got to have a name. Okay, so atoms. So that's a Greek word. And then a little while later, Democritus, who is a Greek philosopher, made this statement. This is translated, obviously, because he spoke Greek. But if you break a piece of matter in half, and then in half again, and so on, how many breaks will you be able to make before you can break no further? And that is the idea of an atom. It's something that is unbreakable, something that is elementary, meaning the simplest thing. All right. And then nobody really thought about atoms for about 200 years. No, sorry, 2,000 years. It was a very long time. We had the Middle Ages. There wasn't a lot of technology. It was, everybody was just trying to survive for the most part. Until about the 1800s, when a man named John Dalton started to investigate gases. And he learned that these gases were made out of elementary particles. Again, that means the simplest particle, the smallest piece that you can find. About the same time, Thomas Thompson discovered a few things, including the electron. Sometimes in the literature, you see him referred to as J.J. Thompson with a P in it. It's the same guy. I don't know why sometimes his name is spelled differently. But anyway, so Thompson discovered electrons and developed something called the raisin and the pudding model of atoms. Now this is a little confusing for Americans because he was British. And pudding means something totally different to them than to us. So this picture sort of is supposed to demonstrate this. Whenever a British person says pudding, you should think cake, because that's kind of what they mean. Okay, so a bread pudding is something where you've got like raisins with like this cake-like substance around it. And he envisioned having like a spherical pudding. Okay, so it'd be like, to an American, it'd be like if you took a piece of carrot cake, with like the raisins in it, and made it into a sphere, like a ball. That was his vision. And he said the little raisins are the negative charges. So the little raisins are the electrons that he discovered. and the positive cake just sort of distributed around the rest of the atom. So he thought that the electrons were a condensed positive charge and that the rest of the atom was just, you know, a vague positive space. It turned out to be wrong, but we didn't know it at that time, and it would take quite a bit of years before that theory was proven incorrect. In the meantime, in Dalton's work, one of the things he discovered is that we have ratios of elements. So when we were looking at the reactivity videos last week, we saw one where they did this with water, and they generated twice as much hydrogen as oxygen, because the formula for water is H2O, right? So oxygen's on the left and the H is on the right. And we know that because there's twice as much on the right as there is on the left. And we also tested it in that video. You can light oxygen on fire and it doesn't make any particular sound, it just burns things. But hydrogen makes a really loud, like, barking noise. So anyways, it doesn't matter where your water comes from. It doesn't matter if it's dirty or clean. It doesn't matter, well, it doesn't matter at all. It's always going to have this ratio of 2 times the amount of hydrogen as there is oxygen. Now, if I put in hydrogen peroxide instead of water, this would be highly dangerous. Don't do it. But if we did, we would get an equal ratio of hydrogen and oxygen. Okay, but it doesn't matter where my hydrogen peroxide comes from. This would always be true. And so we call this the law of definite composition. It means that no matter where the sample comes from, it's always going to be 1 part oxygen and 2 parts hydrogen. Okay. So that comes from Dalton's theories. So he has 4 postulates. All right. And these are a foundation for the modern atomic theory. Basically, each element is composed of really small particles, and we call them atoms. Each atom is different. So if you have an atom of oxygen, that's the one shown in red here, it's completely different than an atom of nitrogen, and they behave totally differently. Number 3, which turns out to be halfway right, says that elements cannot be changed into other elements. So I can't take an oxygen and turn it into a nitrogen, except for the fact, he didn't know this at the time, it happened way later when Marie Curie was doing her work, except when you do nuclear chemistry, which we get to learn about in the next chapter. Then you can actually change them from oxygen to nitrogen, but there's no chemical way to do that. So we could just think of this as, you know, there's no chemical change that will turn oxygen into nitrogen. Okay. However, I can combine oxygen and nitrogen. They reverse them here. That's the one thing I don't like about this graphic, right? We can combine oxygen and nitrogen and make a compound, all right? So again, a compound, just to remind you, is 2 or more different elements connected to each other, right? It is a pure substance, if you recall from chapter 1, just like elements can be pure substances, all right? So these are the 4 postulates of Dalton's atomic theory. Most of them turn out to be right. Number 1 is definitely right. Number 2 is definitely right, although it turns out there is some variation between 2 different kinds of oxygen, okay? We're going to learn about that in this chapter. Number 3 is mostly right. There's no chemical way of turning oxygen into nitrogen, but there is nuclear chemistry, which isn't a chemical change exactly. We're going to learn about that in chapter 5. So, you know, hold on to your hat. It's very exciting. And then number 4 is definitely true. You can take 1 oxygen, 1 nitrogen and make NO. Now, on the other hand, the law of constant composition comes into play. This is a 1-to-1 ratio, but I could take 2-to-1 and make a completely different compound. Okay, one is laughing gas and the other one kills you. So, you know, totally different things. This leads us to the law of multiple proportions. Okay, so a similar example is water has 1 oxygen, 2 hydrogen, whereas hydrogen peroxide is 2 hydrogens and 2 oxygens. So this is a 2-to-2 ratio, whereas the ratio between oxygen and hydrogen is 1-to-2 over here. So the law of constant composition means that if we find water anywhere, it's always going to be a 1-to-2. The law of multiple proportions says that you can take the same elements and mix them together in different proportions and get completely different substances. For example, I would totally drink water. It's delicious. I love it. I would never drink hydrogen peroxide. It will kill me. Okay? So that's the difference. Even just having one extra oxygen, it completely has different properties. It's very, very corrosive. It would sort of digest your tummy, which is not yum. That's bad. All right. Same thing here. Carbon and oxygen in a 1-to-1 ratio creates carbon monoxide, which is highly poisonous. Carbon dioxide is just fine. You breathe it out all day long and it doesn't cause you any problems. Okay. That's what the law of multiple proportions says. If you have different proportions of your elements, it's going to make different substances. Okay. So I said that Thompson discovered electrons. Okay. He did it by inventing a technological device which we should all be very thankful for. It's called the cathode ray tube. Okay, this is sometimes abbreviated as CRT. The cathode ray tube led to the discovery of electrons because basically it turns out if you put a screen, all right, so that normally you don't see anything in a cathode ray tube, but if you put a special screen in there, it will glow in response to the high energy particles that are in here. So a cathode ray tube is just a piece of glass with a gas trapped in it, and you can hook it up to some wires, right? So like a battery. And when that happens, the gas gets excited, high energy, and it's able to interact with this, what we call a phosphor screen. So a phosphor screen is a way of seeing the cathode ray. Otherwise, the ray is invisible. And so what we're seeing here is this charged matter traveling through the tube. And so one of the first things Thompson did with it was to take a magnet and see what happens. And it turns out that it will attract a positively charged magnet. And the red part is positive, is going to attract this beam. So it bends. That's really strange. We had never seen energy bend before. So this led him to investigate the different properties of the materials he was working with, and he concluded that something negatively charged existed in these particles, and he called it the electron. This happened in 1897. Okay. And the reason that we should be excited about the invention of the cathode ray tube back in the 1890s is because it led eventually to TV, right? So if you've seen those giant TVs, they're kind of old now, but you know, they were like really deep in the back. You had to have the TV stand really far from the wall or the TV doesn't fit. Those were called CRT TVs. You could have seen computer monitors that are the same way, really big in the back. And the reason for that is that the cathode ray tube needs space. So the tube shines its light onto the screen, and what you're actually seeing is the phosphor reacting with the light shining on it. But you needed quite a distance to see that. So those TVs were both very heavy because cathode ray tubes are very heavy, and they had to be really deep instead of flat like our current, laptop screens and computer screens. Those are called LCD screens. Okay, so CRT has given us TV and computer screens and all kinds of stuff. It's really great technology that is still used today in other places for different things. Okay, but they were first used to discover electrons because the beam is attracted to the magnet, so it bends towards it. That means it's negatively charged. So that's how electrons were discovered. Protons were discovered by a man named Ernest Rutherford. And the story goes, now Rutherford was a very good teacher. He had a lot of students, which made huge advances in science during his era. But the story goes that Rutherford devised this experiment, and basically the way he set it up is to use some of Marie Curie's work, which we're going to learn more about in the next chapter. She explored radioactivity, and so alpha particles are radioactive particles, and what they are is a helium atom with a mass of 4, and they also have a positive charge. So we're shooting this beam of particles which has a positive charge at really thin gold foil. Now we used gold foil because it's really easy to make it flat, and you can almost make it like one atom thick. So you want it to be as thin as possible. And it's really hard to do that with most metals, and you can't do it with non-metals. They break, right, because they're dull. So we form this really thin gold foil sheet, and we shoot our positive alpha particles at it. And so the idea was to take J.J. Thompson's model, which says, you know, if you have all these negative charges and you shoot a positive beam of electrons at it, okay, what's going to happen is these electrons are going to be attracted. They're going to want to hang out with these positive particles are going to want to hang out with these negative electrons. They're going to be attracted. And so the idea here, the beam has to keep going. It can't stay, right? So the idea here is you would shoot a positive beam at an atom, and if the atom actually has these condensed negative charges, then it's going to be attracted and it's going to travel straight through. Maybe sometimes you've got a beam that's going to be a little bit off. It might even bend a little teeny bit because it wants to get close to this particle. And if that happens, you're going to get kind of a scattering, we call it, right? So here's our screen, and we end up with positive charge that mostly goes all the way through with a few little outliers from where it was attracted to the electron, right? So that's what you see right here. Now, the thing about it is that when Ernest Rutherford did the experiment himself, he put the screen only in the front because that's where he thought he would see his, you know, glowing phosphor. Again, by the way, alpha particles are another beam that you can't see. They've drawn it here in red so that we have something to look at, but alpha particles, I'm going to write this down because it's really important. Alpha particles are not lasers. Lasers are energy, alpha particles are matter. So they're completely different. You can't see this beam. It's an invisible gas that happens to have a positive charge. Okay. Now, so what actually happened in this experiment is we have our positively charged beam, and what he initially saw seemed to support his conclusion. He hands off the experiment to one of his students, his graduate students, and by the way, they're the ones who do all of the grunt work in science, okay? So this graduate student, who nobody really knows his name as far as I know, didn't really understand the method. He did not understand that the screen was only supposed to go in the front. So he made the screen stretch all the way around with just a little opening where the beam comes in. And this mistake actually led to the discovery of something really, really important. And that is this little beam right here. It's very small. A very small number of alpha particles end up bouncing all the way back or being deflected by a lot, like way over here. The only way that could be explained is if you have a positive beam that is not interacting with a negative particle, but rather is interacting with a positive particle. And so this is fascinating because when two positive particles come in close to each other, they're going to bounce off, they're going to repel. So that's where you get the reflection. Okay, so it's two positive particles coming together causes the beam to be reflected. That's what we're seeing here and over here. This model does not match the raisin and the pudding model that Thompson had proposed that had been around for something like 20 or 30 years. So imagine in your entire lifetime believing that atoms looked one way and then come to find out when they could test it that they didn't behave that way at all. So this was quite a revolution. What we're seeing on the screen here is that most of the particles pass right on through. Okay, so this leads to a conclusion. So the observation is that most particles go through with very little deflection. The beam is the darkest, straight through, right? And so the conclusion from that is that atoms are mostly empty space. That feels weird. We don't really like the idea of empty space. How come you can touch a table then if it's mostly empty space? That's weird. But that's how it is. That's the truth. Oh, what the heck? All right. So this beam that got reflected is important. So some alpha particles are reflected. The only conclusion we could draw from that is that the center of an atom is very dense and very positive. You can't have a reflection like that any other way. So Rutherford's experiment, we call this the gold foil experiment for obvious reasons, showed conclusively that the raisin in the pudding model was not true. Atoms did not have condensed negative charges. What they have is condensed positive charges. And most of the rest of it is empty space. All right. Neutrons are the last subatomic particle, and they were discovered much later, in 1932 by a guy named Chadwick. All right, and the reason that neutrons were the last thing to be discovered is because they don't have a charge. They're neutral, which means that when you put them in a magnetic field, they are not attracted in any way. So this is about radiation, but the same kind of experiment is done with electrons, right? So the electrons are going to be negatively charged, which means they're attracted to the positive end of things, whereas the protons would be attracted to the negatively charged end, so that's the red beam. Neutrons, on the other hand, have no charge. So they're just neutral, N, no charge. That means that when you put them in a magnetic field or you put a magnet up next to them, they don't get bent in either direction. So it was a long time to identify neutrons. It was not a quick process. All right, but the guy that did that was Chadwick in 1932, doing something we call the oil drop experiment. Okay. So this is a summary of everything we know about protons, neutrons, and electrons at this point. The protons and the neutrons are in the nucleus. Nucleus means center, right? You might have heard that phrase in like biology class, but the nucleus is the center of the atom. All right. That's where the protons and neutrons are. And as it turns out, they are the things that give atoms mass. You'll notice that we have an atomic mass of 1.0073 for protons, and neutrons are almost exactly the same, a little heavier.